Hello, fifth graders. We're going to continue to explore the concept of multiplication of fractions with the understanding that it is very simple to do. But my job is mostly explaining why things are the way they are, not so much how to get the right answer. Let's take 2/3 times 5/7. Look how simple it is. Multiply across the top and bottom. We can put this into a general formula. A over B times C over D is A times C over B times D. There's no need for a common denominator. In the course of my explanation of why multiplication works the way it does with fractions, I'm going to do something similar to common denominator as you've seen before, and I'll do again today. But let's understand that multiplying two fractions is very simple. Both of these fractions, 2/3 and 5/7, they're each less than 1, which means that the answer, the product of the two numbers, is going to be less than either one of them. The 10/21 is less than 2/3, and it's also less than 5/7. And that's perhaps one thing that takes a little getting used to at first. When we learn multiplication with whole numbers, when we're in 3rd and 4th grade, as long as both numbers are greater than 1, both whole numbers greater than 1, we get a product greater than either of the original numbers. But that's not always the case with fractions. In this case, the two fractions being both less than 1, we get an answer, a product less than either one of them. And hopefully the explanation will make this clear. Another consideration which goes all throughout mathematics at whatever level. I could show you some examples. Don't have an infinite amount of time, but if I did, I'd show you in 5th grade how 8th graders taking Algebra 1, a high school math course, often will have to learn to distinguish between addition and multiplication. It's one of the big challenges of learning math at any level. There's a whole set of rules for addition and subtraction, and a completely different set of rules and understandings as well for multiplication. If we were to add 2/3 and 5/7, we would get an answer greater than either one of them. In fact, an answer greater than 1. But with multiplication, it's a different operation, an entirely different thing that we're doing with the two numbers. So let's take a look now at why 2/3 times 5/7 is 10/21, and we're going to do that two different ways. I've put the formula back on the board at the top. Also, last time I neglected to say that the denominator can never be 0 in a fraction, so B and D cannot be 0. Otherwise, just multiply across the top and bottom. Very simple. We know the answer here is 10/21. But why? Well, the first explanation is one-dimensional. It's on a number line. And we're going to use the concept of the word of to associate the word of with multiplication to understand what it means to multiply fractions. So 2/3 times 5/7, we're going to think of it as 2/3 of 5/7. And once you do that, you get that sense that the answer is going to be less than 5/7. 2/3 of something is less than the whole thing. And we're also going to realize that 2/3 is 2 times bigger than 1/3. And we're going to use the associative property of multiplication, which applies to fractions as it does to whole numbers. The associative property says that we can, it's a little different than the commutative property. The commutative property says 5 times 6 is the same as 6 times 5. You can change the order. The associative property is about the grouping. So rather than do 2 times 1/3 and then times 5/7. We can take 1/3 of the 5/7 first and then multiply that result by 2. And that now brings in this idea of an equivalent fraction, because what is 1/3 of 5/7? That's a hard thing to conceptualize. It's a hard thing to consider on the number line. But if we convert 5/7 into an equivalent fraction of 15/21, then it becomes a much simpler matter. And we know that anytime we have a fraction, we can multiply the top and bottom by the same number to get an equivalent fraction, the same point on the number line. Because of this denominator of 3, I'm going to multiply the top and bottom of the 5/7 by 3. And again, this is not necessary to get the answer. This is only necessary to understand why we can multiply across the top and bottom. So now we have 2 times 1/3 of 15/21. And at this point, the question, what is 1/3 of 15/21, should answer itself. It should be obvious. 1/3 of 15/21 is like 1/3 of 15 pencils. 1/3 of 15 pencils is 5 pencils. 1/3 of 15 people is 5 people. So 1/3 of 15/21 is 5/21. Using the associative property, we can do that first. So that now we have 2 times 5/21. And this also sort of answers itself. What is 2 times more than 5/21? It's 10/21. Now, please don't think that when you're multiplying 5/21 by 2, you multiply the top and bottom by 2. That doesn't get the job done, because, as I just said, if you multiply the top and bottom of a fraction by the same number, you get an equivalent fraction. You don't get a number that's twice as big. If you want the number that's twice as big as 5/21, that's 10/21. And what we could do, if you're curious about this, is to multiply 5/21 by 2. You can represent that 2 as 2 over 1. 2 over 1 is 2. And multiply across the top and bottom, and we have 10/21, the answer that we knew that it was. Now, if we were thinking of a number line, we would have the 5/7. 5/7 is more than half. 4/7 is more than half. So maybe 5/7, I'm just going to estimate, maybe 5/7 would be something like that. And we want 2/3 of it. So we would have to think about dividing this distance into 3 equally sized pieces and then going to the second one. So it would be something like that, right? But what are those numbers? Well, this is where converting the 5/7 into 15/21 comes in. If we think of this as 15/21 and we've divided that length into 3 equally sized pieces, then this would be 5/21 and that would be 10/21. And that point there is 2/3 of the length of the line segment that is 5/7. So there's one way to explain why we multiply across the top and bottom, why 2/3 times 5/7 is 10/21. This is a one-dimensional explanation. It takes place on the one-dimensional number line. Lines and line segments in math are only one-dimensional. They only have length. They don't have any width. We have to draw them with width to see them, but there's no this way on a line. There's only that way. It's one-dimensional. But we're going to now provide a two-dimensional explanation of why 2/3 times 5/7 is 10/21. I've constructed a square on the board, and we are going to say that the area of that big square is one square unit. We're going to say that each side is 1 unit. And the area of any rectangle, a square is a rectangle, of course, is length times width. So if each side is 1 unit, 1 times 1 is 1, it's 1 square unit. The area of this big square is 1. That is a key understanding in this explanation of 2/3 times 5/7. Let's take a brief look back without looking at any rectangles, but you could easily imagine one. Let's say you had a rectangle that's 3 inches by 5 inches. The length is 5 inches and the width is 3 inches. Well, we learned in 3rd grade that the area of that rectangle is 15 square inches. We associate multiplication with the area of rectangles, and that's what we're going to do here with this square. It is a foundational assumption in geometry and in math. Every 3rd grader should associate areas of rectangles with multiplication. If you have a rectangle that's 10 inches by 7 inches, the area would be 70 square inches. Now, when I constructed this square, we're assuming that each side is 1 unit, but I actually strategically made each side 21 inches. And if you recall, the number 21 figured into our understanding of the multiplication in 1 dimension. It also figures in here with the 2-dimensional explanation. Now, our problem is 2/3 times 5/7. And let me erase this for now. The denominator of the answer is 21. And also along the way earlier, if you recall, I converted 5/7 into 15/21. And that's why I made each of these sides 21 inches long. Because what we're going to do now is subdivide this square, whose area is 1. We're going to subdivide it into 21 congruent rectangles. Congruent means they're the same size, the same shape, identical rectangles, just in different locations. We're going to represent the area of the square exactly with 21 rectangles. And the reason it's going to be 21 is because of those 2 denominators of 3 and 7. We're going to subdivide the vertical sides. We're going to divide those vertical sides into 3 equally sized pieces, and then we're going to divide the horizontal sides into 7 equally sized pieces, and that'll create the rectangles that I just described. So let me do that. Just thought I'd give you a quick peek before it's done. I've divided the vertical sides into 3 equally sized pieces. From here to here, 1, and then 2, and then 3. Okay? And I'm about to do a similar thing to the horizontal sides, only 7 equally sized pieces. So here's the finished product. Markers on a board like this are a little bit unforgiving. Sometimes I accidentally erase part of the line segment that I put there, but this is a pretty good job. If you had a piece of paper, a sharp pencil, or an ordinary pen, and you measure carefully with a ruler, you could make it look even better than this. Of course, you'd need a pretty big piece of paper to, to make it 21 inches by 21 inches. Maybe centimeters would work on the other side of the ruler. That might get the job done on an ordinary size piece of paper. Yeah, perhaps. I think so. 21, oh no. An ordinary piece of paper is only about 20 centimeters wide, so you couldn't do it on an ordinary 8.5 by 11 sheet of paper. Anyway, let's now look at the horizontal sides of the square, the way I did with the vertical ones a moment ago. It's 7 equally sized pieces, starting at the end here and counting 1, 2, 3, 4, 5, 6, 7. So going back to that 3rd grade concept now, we've got 7 rectangles across and 3 up and down, so we don't have to count them. There are a total of 21 rectangles, congruent rectangles. They're all identical, that now are completely paving, like tiles on a floor. They're completely paving the area of that square, which is 1. So now what we need to do, I'm going to take a red marker and indicate along the vertical sides, one of the vertical sides, a length that is 2/3. Well, that length right there is 2/3. Remember, each side of that big square is 1, so I divide it into 3 equally sized pieces. So from here to here is 2/3. And the 5/7 along the horizontal side at the top I'll use 1, 2, 3, 4, 5. So that length there is 5/7, 2/3, and 5/7. So can you guess what I'm going to do now? I'm going to create a rectangle that is 2/3 by 5/7. I'm almost there. All I have to do, again with this red marker has kind of failed me. I thought it was really new and would work. Let's see. I'm going to now, on top of the old black lines that were there, I'm going to trace with red. Doesn't look like it's there. I think you can maybe just barely see that. I thought red would be very visible, but it kind of is not as dark as I wanted. So how about if I try blue? How's that? Yeah, that might be a little bit better. So 2/3 this way. And then 5/7 across. What we have is a rectangle that's 2/3 by 5/7. But what is its area? Well, remember, we associate as a foundational assumption in geometry and arithmetic with multiplication that the area of a rectangle is length times width, in this case 5/7 times 2/3, and that works with fractions as well, because what we have here is a rectangle that's 2/3 by 5/7, but look at its area. What is its area? It's 10 of those rectangles, right? And again, we wouldn't have to count them, but let me sort of indicate them like this. Our rectangle, which is 2/3 by 5/7, is 10 of those identical rectangles that are paving the entire big square. Now recall, there were 21 of those in the entire square. And our rectangle, 2/3 by 5/7, is 10 of those rectangles. It's 10 out of 21. You see? 10 out of 21 is 10 21sts. And that's the two-dimensional explanation of 2/3 times 5/7 being 10 21sts. This explanation, the two-dimensional explanation, is often done in the textbooks, but the problem with it is you only see the finished product. And it's kind of hard, even for me sometimes, to see exactly what is trying to be demonstrated by those diagrams. But when you see it created from start to finish, I think it's a very, very powerful explanation of multiplication of fractions. So 2 different ways now we have seen why 2/3 times 5/7 is 10 21st. But to get to the result is very simple. And going forward, of course, you're not going to explain why when you are tasked with these fraction multiplications. You're going to get the answer, but you're going to believe in that answer because of these explanations. I see we're at about 20 minutes. I would like to do one other thing, and that is to think about the commutative property of multiplication. It applies to fractions as well as to whole numbers. If we were to reverse the order, as far as the two-dimensional explanation, reverse the order of the multiplication, well, if we sort of flipped that big square over so that the 2/3 was at the top and the 5/7 along the side, that rectangle that's 10/21 would of course stay the same. Right? Just imagine, see, I'm thinking of it as 2/3 times 5/7. So it's this side, this length of here, this 2/3 times the 5/7. But if we want to reverse the order and put the 5/7 vertical, we can do that. We can rotate the square, and then the 5/7 would be along the side and the 2/3 would be at the top, but of course it would be the same area and the square would be the same area. So the commutative property of multiplication is very intuitive in terms of rectangles. Just rotate the rectangle, its area doesn't change, but then we see the length and width are different. And the order has been changed. What about the one-dimensional explanation? Let's take a look at that. And I really could have done this earlier when we were looking at the one-dimensional explanation, but this will be how we close out this video now. By, instead of thinking of 2/3 times 5/7, what about 5/7 times 2/3? Well, the commutative property tells us that the answer is the same, but let's go through the one-dimensional explanation. We would see this as being 5 times 1/7 of 2/3, right? 5/7 is 5 times 1/7. So 5 times 1/7, and then of 2/3. And again, we want to make an equivalent fraction here now because of that denominator of 7. We will multiply the top and bottom here by 7 and get 5 times 1/7 of 14/21. Right? You see how this is going to come out now? What's 1/7 of 14/21? It's 2/21. Right? 1/7 of 14 is 2, so 1/7 of 14/21 is 2/21. So we have 5 times 2/21, and that, of course, is 10/21. 5 times 2/21 is 10/21. So if you're not convinced by now that 5/7 times 2/3 or 2/3 times 5/7 is 10/21, I can't do anything else. That's about it. Those are the only ways I can think of to convince you that it works. And coming up with the answer is very simple. So we'll call it quits for now. Take care, 5th graders. Multiplication of fractions. It's a wonderful topic. Bye-bye.